Hi guys, Mohit here. This is the last part of CUDA Graph series covering topics related to memory and things that are important when you actually start using CUDA Graphs. In part 1, we started with fundamentals of CUDA Graphs, where we looked how normal CPU to GPU execution normally looks like, where kernel launch overhead comes from, what CUDA Graphs actually do, and how capture and replay help reduce that overhead. Then in part 2, we focused on why CUDA Graphs matter for inference, looking at where they help in inference workloads, especially around decode, repeated kernel launches, CPU overhead, and the challenges that come with dynamic inference workloads. Now, in part 3, I want to finish off with some deeper concepts that are important to understand once you start working with CUDA graphs. We will mainly look at three things. The first is how memory works with CUDA graphs. The second is what can and cannot be safely captured with CUDA graphs. And the third is what happens when a graph needs to change after we have already created it. So let's start with the first one, which is how memory works with CUDA graphs. So one important thing about CUDA graphs is that when we replay a graph, we are not running our original Python or CUDA code again from scratch. During capture, CUDA records specific sequence of GPU operations, right? And those operations can reference specific locations in GPU memory. We have talked about this before. So let's take a simple example. Imagine we have an input tensor stored somewhere in the GPU, and we capture a sequence of operations that uses that tensor. So when we replay the graph, those captured operations expect their memory references to still be valid. Okay, so this is the reason why stable memory addresses are important with CUDA graphs, but this doesn't mean our input data can never change though. Whenever we get new input, we copy that new data into the same buffer and still replay the graph. So the actual data can change between the replays, while the memory address that we have, that the captured graph expects to stay stable. And there is another side to this: memory allocations during graph capture. So examples like frameworks like PyTorch have to carefully manage allocations associated with these captured graphs. This can also introduce a trade-off though. If we are actually capturing multiple graphs, each graph potentially having its own memory requirements, our overall GPU memory usage can increase, right? In some situations where they use memory pools can be shared between graphs when their executions patterns make that safe, which can help reduce this overhead. So the main thing to understand here is basically CUDA graphs don't just care about what the operations execute, right? Those captured operations also depend on where their actual data lives in the memory. That's why stable memory addresses, static buffers, and memory pool management becomes important once you start using CUDA graphs in like real workloads. Now, the next question is, can we just put any operation inside a CUDA graph capture? And the answer is no. CUDA has specific rules about what can safely happen while a stream is being captured. If we look at this example, we begin the stream capture and then submit a normal asynchronous GPU work. Okay, the kernel launch can be captured as a node in a graph, and an asynchronous memory copy can also be captured when used in a capture compatible way. And as more GPU operations are submitted, CUDA captures these operations and the dependencies between them to build the graph, right? Now, the problem starts when an operation doesn't fit safely into this capture semantics. So the major example is synchronization. If we perform certain synchronization operations during capture, especially operations that involve or synchronize captured work in prohibited way, the capture can become invalid. For example, calling CUDA device synchronize during capture forces the CPU to wait for the GPU work, which can break the capture, right? Another important case is CPU side logic, meaning let's say we copy a value from the GPU back to the CPU, inspect its value in Python or C++, and then decide which GPU operation to launch next. That CPU decision itself isn't something ordinary CUDA graph stream can capture and turn it into a normal graph node. The graph captures the GPU execution path that actually occurs during the capture. It doesn't automatically capture arbitrary host side control flow and make a dynamic replay every single time. Okay. There are also CUDA APIs and operations with specific capture restrictions. So whether something is safe depends on the operation and the capture mode being used. If a prohibited operations occurs, the capture may fail or become invalid, right? Meaning we can't simply finish it and replay it as a valid graph. So the important mental model about this is CUDA graph capture is not record anything my program does basically, right? It captures a compatible sequence of GPU work and its dependency so that this execution structure can later be replayed again efficiently. That's why before graphing a real workload, we need to know which parts to capture safe and which parts need to stay outside the capture region. So far, we have talked about CUDA graphs as something we capture once, prepare, and then replay many times. But in real workload, things may need to change. Let's say we already have this executable graph with kernel A, kernel B, and kernel C. The simplest case in this is when you want to change something about an existing node. For example, we might want to change kernel B to use different launch parameters. Let's say CUDA lets us update certain node parameters directly. In this case, we keep the same executable graph and just update what a particular node needs. But sometimes we have newer version of the graph with more changes. For this, CUDA provides CUDA Graph executable update. Basically, CUDA compares the new graph with the executable graph we already have and checks whether it can update the existing one instead of creating everything again. If the changes are compatible, CUDA can update that existing executable graph and we can continue using it normally. But if the graph changes too much and, for example, its structures or topology changes in incompatible way, then the update can fail, right? So for that case, we may need to prepare a new executable graph that represents the new workload. So there are really three ideas here. If there is a small compatible change, you just update the node. If there is a compatible graph level change, we try CUDA Graph execution update. If the changes are incompatible, you create a new executable graph. Now, these are useful because a workload doesn't always stay exactly the same, and CUDA gives us many ways to handle some changes without rebuilding every single thing again. And that's basically it for the part 3 of CUDA Graphs. And in this part, we look deeper into how memory works with CUDA Graphs, what can and cannot be safely captured, and how CUDA handles graph when parts of the workloads need to change, right? From here, we are pretty much done with the CUDA Graphs fundamentals I want to cover in these 3 parts. So that will be it for this one. See you in the next video, and thanks for watching.